Hi everyone, my name is Yuri Kalinin. I am the chief auditor of the Far East branch of Sberbank. I'm in charge of internal audit, and today at this unusual event I'd like to talk about what's GRAKN and how you can apply it. Let's take an example. We have an audit task, specifically compliance. And let's start with the basics. What's a GRAKN? That's by nature a database, because turns out that in the 21st century there are tons of different databases around us of all kinds and in different spheres of lives, but mostly those are relational databases, and that's no surprise. Of course, there are many positive features of relational databases, but they do have some advantages as well. For example, one of the disadvantages is that they don't take account the character and the nature of ties in their directions. In addition, it's not always convenient to describe certain complex structures of data with tables. For example, certain complex social networks or high-level logistics. And for those tasks, they usually apply different sort of database, the graph-oriented database. And as you might have already guessed, GRAKN is the example of that sort of database. That is a deductive database with the implementation of machine thinking, machine learning, to simplify the task for data processing and task processing, so that we could apply AI for that. So we could think, make ties in our head, and that's natural for a human being. We do it on a daily basis, or even sometimes every second for the smartest of us. But when you see a green light in a street, for example, you can cross the street. Or you can see the hot stove, so that means that if you touch it, you'll get burnt. Or look at this slide, the logical consequences, causality. Pushkin was born in Moscow, Moscow is in Russia, so Pushkin was born in Russia. This sort of cause and effect thinking is habitual for us, but for the machine, this sort of approach has been unavailable until lately. So the developers of GRAKN.AI decided to remedy this. And they have implemented their databases based on this analytical thinking mechanism. So what do we get from that? What sort of advantages do we get from that? I mean, first of all, it allows us to save the use of RAM, and memory. You don't need to store all of the data in the database. You just need to store the portion of data and, of course, the rules that ties those data. For example, color samples. You don't need to have all of the color samples in your database. You need to have the RGB, red, green, blue, and then the rule using which you can mix those colors and get extra color samples. In addition, this approach, the use of GRAKN.AI, allows to build quite powerful, while flexible, systems of expertise that can use data from different branches of data, different sorts of data sets, while data is connected. Therefore, adding data into one domain leads to the update in the data in a different domain. Like a detective. Imagine you're watching a detective movie. You get to know certain facts about the situations. You see the evidences. First, you don't see them as significant, and you might not even notice them at time. But the more data you get from different sources, the more you see the full picture and the better you can tie them. And therefore, based on the full picture, it is possible to make a conclusion on who is the suspect. So that means that adding data into one domain means to lead some conclusion or other data in a different domain. Unfortunately, though, GRAKN doesn't have any built-in speech analysis tools or other NLP tools. So if you want this database to work, you need to treat data in a specific way for the database. The data should be delivered as entities and ties between entities. The rules that allow transferring one sort of ties into different sort of ties. So let's look at the example. After that, you will probably have no questions about what entities and ties we are talking about. Let's take a look at the following task. For example, we are the auditors or the security service of a bank. Let's call it GRAKN Bank. And one of our tasks, in addition to everything else, is to avoid the conflict of interest between our employees when those conflicts might happen. When, for example, in different positions that people interact, there are people who are relatives. Imagine an office, and there is a mother and a daughter. So the mother makes an operation, daughter has to confirm that operation. They might reach certain agreement because they're relatives, and then they might get into fraud, and fraud is always fun. Or one of the employees is constantly making certain mistakes and errors, and the other employee is covering those errors because, again, they're relatives or friends or whatever. So, therefore, we need to avoid the number of this sorts of situations. How can we do that? When an employee, for example, is applying for the job, we might request that employee to actually fill the certain questionnaire, noting where the relatives of this person work. So, for example, if some relatives of this person work in the same office, we can consider that or even reject the application of this potential employee. But of course, the applicants understand the situation and then they intentionally lie or conceal some information. So GRAKN, since it can think in a way automatically, can help us to reveal this sort of hidden ties. How? How can it do it? Let's look at a simple data scheme for GRAKN. There are two entities here. Person, and that is an actual people, an actual person, our employees, for example, and this also includes the relatives of our employee. And we have the entity called company, which is all of the organizations and businesses where actual people work. So the entity can have any set of attributes. For example, the attribute name. And by the way, the attributes can be shared, or the attributes can belong to several entities, such as name, for example. In addition to attributes, the entities also have ties with each other. For example, in this case, the ties are mentioned with these rectangles. There are 4 of them, but we can split them into class, which is labor relationships and actual relationships of relatives. So, the symmetry here is when both entities are connected to one another equally. For example, friendship. I am your friend and you are my friend. So that is equal relationship, not hierarchy. However, if we speak about hierarchy, then the ties are non-symmetric. So in this situation, non-symmetric ties is when we have the employer and the employee, or parenting relationship, when we have a kid and a child. Oh, sorry, the kid and the parent, of course. By the way, the relationship are not necessarily bilateral. They can be multilateral, and GRAKN supports that. But we will be, for the sake of simplicity, speaking about bilateral relationship. We have figured out the structure of the database. Let's fill the structure with data. But before we do that, let's talk about the language that we're going to be using to interact with our database. For that, we have special sort of language, declarative language called GRAKL. The point of GRAKL, it's a query language. It's human read and human interpreted statement. Query language, every query starts with a link to a notion. Next, we define the type of that notion, and we list the properties of that notion. And we use the ISA operator for the notion, and for its properties we use the operator has. Every statement ends with the hyphen, and you can split the statements in shorter or longer. Sorry, it ends with semicolon, of course. Those of you who are watching the presentation now, they can easily figure out that in this particular case, we're requesting GRAKN to actually extract all of the persons who have the name Bob and who have certain phone number. Okay, I think that is pretty clear for you. So let's look at the sorts of data that we can operate with. For example, we have 3 tables. This is the table of our persons, and we see their properties and where they work, if they're employed. Second table is organizations, and you see those organizations in the table. And the last table is relations, showing what kind of sibling relationship is between our persons. This is the table for relational databases, but let us transfer it to the language that will be clear to GRAKN. That's pretty straightforward. If we want to look at the entity of companies, we see that a certain entity is a company. We have the operator is a, and we also have the operator has, and we assign all of the attributes to the notion of company, of the entity of company. If we want to add certain properties to a person, we should use the operator is a person. So you see how it works. And then we can use the operator has to add properties. For example, has name, gender, born, has name, has gender. So you see that in this case, our entities of persons and organizations are tied with the relationship of employment. So we have the person, which is an employee, and we have the company, their organization, that is an employer. Using this sort of logics, we can represent all of the data that we have here. So this is the script, which can be split into 4 parts. First, the declaration of persons, then the declaration of employer, then we can define all of the employment relationships, and then all of the sibling relationships. Then, with the GRAKN utility, we can actually visualize the data, and this is the graph that we see. Pretty cute, isn't it? Therefore, with the rectangles here, we highlight the entities. And we see these arrows as connections between these entities. So what can we say? We can say that things in our organizations are pretty fine. We have 3 employees and they don't have any conflicts of interests because they don't have any siblings working in our company. But imagine, for example, Mr. Ivanov here has a daughter. The daughter got married, changed her last name, and she decided to work in her father's company, in our GRAKN Bank. But of course, having known that we might not employ her because she is the daughter of her father, she actually only informed us about the name of her mother. So let's see how that works in terms of our database. So we have this Miss Sidorova, and she says that Miss Ivanova is her mother, and she doesn't say that Mr. Ivanov is her father. Let's see how it looks in the graph. So Sidorova has tie with Ivanova. Ivanova works at the company called Daffodil, Ramashka. So we can easily employ Sidorova, Miss Sidorova. But we are auditors with a keen eye, and we see that Ivanova, who is the mother of Sidorova, also is a wife of Mr. Ivanov. So we are all adults, and we can actually contemplate and understand that Sidorova most probably is Madame Sidorova is most probably the daughter of Mr. Ivanov. But we will not be actually looking into the papers in every single case, so we need to teach our database to think just the way we would think, and GRAKN allows us to do that. Let's see how. We can actually set a rule. Here it is. If X and Y are married and either X or Y has connection sibling relationship with the Z, then also if X has sibling relationship with Z, then Y also has sibling relationship with Z, if X and Y are married. So this sort of hidden tie can be easily revealed with GRAKN. It's not that we have imbued it into the database, but we know about it. I think those of you who are the most attentive and those of you who are pretty much aware with SQL databases will ask, why do we need GRAKN? I mean, SQL could do this, couldn't it? I would partially agree with you. SQL can definitely help you search the task of looking for indirect ties. I mean, the ties that are connected to other ties. But in the case of SQL, the operator that is executing the query must have some clear understanding about the interactions of data from different domains, meaning knowing how the data in the table can be tied. In GRAKN, for example, somebody defined the connections before you, so you only need to ask a question to the database. Please show me all of the siblings in this entity, or show me all of those working in a certain organization. So GRAKN knows how to tie those data sets, those pieces of data. But in life, more often than not, we are more interested in a different sort of ties and connections. The probability connections, the probability ties, meaning ties that could be or could not be, with a probability of 20 or 100%, with a probability of a 20 or 100%. Let me give you an example. For example, I own a vehicle, a car. So what's the probability that in the upcoming 6 months I will be fined? You will probably look at certain stats saying that the probability is, for example, 5% that I'll get a ticket. But what if you know that the horsepower of my car is 300 horses and I have mechanical transmission? So that, in your view, might, for example, increase the probability of me getting a fine. And what if you know that I have the special detector for police radars in my car? Will that affect your probability estimate of me getting a ticket? I mean, the probability of your estimate directly relates to the context in which the entity exists, the entity for which we're looking those ties. So why don't we take that context or part of it and use it as the input vector of features? So the actual existence or absence of ties can be used as the binary variable, target variable. So therefore, all of the task of searching a tie bottoms down to simple ML task. When we're creating a classificator, that will actually give us a prediction of a class. So, for example, we know that we have the probability of the tie and connection existing. With the case of GRAKN, in the context, we get the context not as in the classical ML environment when for the input you kind of send the properties of entity. Here you send not only the properties of entities, but also the properties of entities connected to this entity. Do you get it? So in the context, we can actually include the properties of connections. So it is possible to regulate the depth of connection, second knee, third knee, etc., etc. The deeper you use the context, the more the probabilities that you will be able to find some exciting connections. You can see this on the graph, I believe. As a context, you may use not only the data that you have actually put into the data, but also the data that you were able to output. I told you about the sibling relationship. You can find that sort of ties and include them into the context. Therefore, GRAKN allows you not just solve the sort of task, but it helps to solve this very urgent problem of ML, which is the lack of data. We do understand that Google or Yandex, or you name it, Amazon, all of these big players indeed use large-scale computing. Yes, they have the cutting-edge technology and algorithms, but their main feature, winning feature, is that they have an access to the ton of information. And any ML expert will tell you that success in ML depends directly to the volume and quality of that volume of information. So the use of GRAKN does not solve all of the ML issues, but you can use GRAKN also for other tasks, such as development of expert systems based on GRAKN guides, financial tools. There's another exciting case to use GRAKN for text mining, or you can write a guidebook with GRAKN, or a manual. I have described that in detail in my, they are all described on the GRAKN.AI developers page and also in their GitHub. To conclude, I want to leave you with this. It's not necessary to use GRAKN. You don't have to use it. But it would be exceptionally useful to know that the tools of such nature exist, and it's good to know how to use them, because this sort of tools like GRAKN and like graph-based database are the future of AI. Therefore, I conclude. Thank you.